Welcome viewers. We are now beginning module 29 of this course on econometrics, and this module will deal with testing of several coefficients of the multiple linear regression model in a joint manner. To begin with, as earlier we consider the three variable model yi regressed on x2i and x3i. Suppose we consider the null hypothesis that beta 2 plus beta 3 is equal to 1 and the alternative hypothesis beta 2 plus beta 3 not equal to 1. We will now test whether this holds good or not, and we recall that in order to test about these coefficients, we make use of their sampling distributions. So, we begin by noting that under the null hypothesis, under H naught, beta 2 hat plus beta 3 hat follows a normal distribution with mean 1 and variance beta 2 hat plus beta 3 hat. The reason is that in general, even if H naught is not true, in general beta 2 hat plus beta 3 hat follows a normal with mean beta 2 plus beta 3 and variance of beta 2 plus beta 2 hat plus beta 3 hat. But under H naught beta 2 plus beta 3 is equal to 1. Therefore, we substitute this with the number 1. So, from this step we note that beta 2 hat plus beta 3 hat minus 1, the square of that divided by variance of beta 2 hat plus beta 3 hat will follow a chi-square with 1 degree of freedom. The reason is that beta 2 hat plus beta 3 hat minus beta 2 plus beta 3 divided by standard deviation of beta 2 hat plus beta 3 hat follows a normal with mean 0 and standard deviation 1. So, because we are considering H naught beta 2 plus beta 3 equal to 1, so instead of beta 2 plus beta 3 we put 1 here. So, under H naught this follows a normal distribution, and therefore, the square of this, which is beta 2 hat plus beta 3 minus 1 whole square divided by the square of the standard deviation, which is the variance, that therefore will follow a chi-square. So, that is the first important information that we have. Remember, all this is under H naught. Also, as we have seen earlier, the residual sum of squares divided by sigma square follows a chi-square with n minus 3 degrees of freedom, because here it is a 3 variable model. So, n minus 3 degrees of freedom independent of the chi-square 1 developed earlier. So, as we have seen already in the previous module, drawing upon the important result that chi-square 1 divided by chi-square n minus k divided by n minus k will follow an F distribution with 1 and n minus k degrees of freedom. Here obviously the value of k is 3. So, we substitute and we write n minus 3, and so we develop the test statistic chi-square with 1 degree of freedom divided by 1, that is implicit, all upon chi square with n minus 3 degrees of freedom divided by n minus 3, following an F distribution with 1 and n minus 3 degrees of freedom. And therefore, we write in terms of our test statistic beta 2 hat plus beta 3 hat minus 1 square divided by variance of beta 2 hat plus beta 3 hat, that is the chi square in the numerator, and all this divided by RSS, residual sum of squares, divided by sigma square divided by n minus 3. So, that denominator is the chi square here divided by its degrees of freedom, and that therefore follows an F distribution with 1 and n minus 3 degrees of freedom. Now, we also have another important result, that is when we have an F distribution with 1 degree of freedom and n minus 3 degrees of freedom in the numerator and denominator respectively, then the square root of this follows a T distribution. So, therefore, we can write that the square root of this follows a T distribution, that is root over of f 1 comma n minus 3 will follow a T distribution with n minus 3 degrees of freedom. Next, we will simplify this further and arrive at a formula which will be easy to handle, and that will follow a T distribution with n minus 3 degrees of freedom. So, that we will be able to form the decision rule on whether to accept H naught or to reject H naught. Students, let us now take a look at how we move from the F distribution to the T distribution. So, we focus on this expression variance of beta 2 hat plus beta 3 hat, that is expanded as variance beta 2 hat plus variance beta 3 hat plus twice covariance between beta 2 hat and beta 3 hat. And from our earlier discussions on the sampling distribution of beta 2 hat and beta 3 hat, we know that variance of beta 2 hat is given by this expression, variance of beta 3 hat is given by this expression, and covariance between beta 2 hat beta 3 hat is minus of sigma square and the rest of the expression. So, that is the composite expression for variance of beta 2 hat plus beta 3 hat. You would have noticed that here we have the term sigma square in all the 3 components. In the denominator also we have this sigma square. So, we can safely cancel this sigma square from this variance expression and this sigma square in the denominator, and that leaves us with RSS by n minus 3. So, RSS by n minus 3 is nothing but the estimated value of sigma square. So, making these substitutions, we arrive at a nice result, beta 2 hat plus beta 3 hat minus 1 whole square divided by, instead of this variance and this RSS by sigma square divided by n minus 3, we cancel out this sigma square in the denominator with all of these sigma squares in the denominator here, and we take out this RSS by n minus 3 and put it as sigma square hat. So, that basically gives us, instead of sigma square, we now have sigma square hat and sigma square hat. So, that gives us the estimated variance of beta 2 hat plus beta 3 hat. Instead of sigma square, we now have sigma square hat, which gives us estimated variance in the denominator. So, we write this as variance beta 2 hat plus beta 3 hat, the estimate of that. Put a hat to denote the estimate. So, that basically follows f 1 n minus 3, and therefore, the square root of this, which is beta 2 hat plus beta 3 hat minus 1 divided by the square root of the estimated variance of beta 2 hat plus beta 3 hat, which is written as the standard error of beta 2 hat plus beta 3 hat. This is our test statistic, which follows a t distribution with n minus 3 degrees of freedom. And this term in the denominator is computed as the square root of estimated variance. What is estimated variance? It is the variance of beta 2 hat plus beta 3 hat. Only difference is, instead of sigma square, here we have estimated it with sigma square hat. And what is sigma square hat? It is RSS by n minus 3. So, we use this test statistic beta 2 hat plus beta 3 hat minus 1 divided by standard error of beta 2 hat plus beta 3 hat, and we carry out the test for H naught beta 2 plus beta 3 is equal to 1 against H 1 beta 2 plus beta 3 not equal to 1. Obviously, this is a two-tailed test. So, we have the t distribution with two goalposts. Here we have t a by 2 n minus 3 degrees of freedom, and due to the symmetry of the t distribution, here we have minus t a by 2 n minus 3 degrees of freedom. These shaded areas, they are jointly called the critical region. So, the decision rule is we reject H naught at the appropriate level of significance if t calculated. What is t calculated? This is t calculated. If that t calculated or calculated value of t, if it exceeds the modulus of t a by 2 n minus 3 degrees of freedom. That means, if this computed value of this t statistic, if it lies either in this shaded part or in this shaded part, then we reject H naught. Otherwise, we accept H naught. Next, we will look at an operationally easy way to handle not only this kind of a test, but other tests involving more than one coefficients in the multiple linear regression model, and that approach is called the restricted least squares approach. Students, now we will take a look at the restricted and unrestricted least squares approach. So, our model is given by this yi regressed on x2 and x3, which is called the unrestricted model. We estimate this model and we calculate the residual sum of squares, which is called the unrestricted residual sum of squares, or URSS. That is the unrestricted residual sum of squares obtained by estimating this model using ordinary least squares as we have learned. But under the null hypothesis, beta 2 plus beta 3 is equal to 1. So, if we put this restriction into the model, then instead of beta 3 we write 1 minus beta 2. So, y is regressed on x2 with the coefficient beta 2, but the coefficient of x3 is 1 minus beta 2 going by the linear restriction. So, effectively we can bring the x3i variable to the left hand side and we regress y minus x3i, say variable zi, on x2i minus x3i, say call it variable wi. So, this is called the restricted model. We estimate this model and then obtain the corresponding residual sum of squares, which is called the restricted residual sum of squares. So, we have an unrestricted model, the original model, and we put in the linear restriction, that is h naught beta 2 plus beta 3 equal to 1, and we obtain the restricted residual sum of squares from the estimate of the restricted model. Then the rest is very simple. We compute the f statistic as restricted residual sum of squares minus unrestricted residual sum of squares divided by the number of restrictions. Obviously, in this particular example q is equal to 1 because we have simply one restriction. So, here in this particular case this q will be equal to 1. That is a chi-square with 1 degree of freedom, and in the denominator we have unrestricted residual sum of squares in general with n minus k degrees of freedom. So, divide by n minus k. Obviously, in this case it will be n minus 3. So, here we will have f distribution with 1 and n minus 3 degrees of freedom. This is exactly the same f distribution which we obtained when we did beta 2 hat plus beta 3 hat minus 1 whole square divided by variance of beta 2 hat plus beta 3 hat. That f distribution is the same as this f distribution. So, what do? We reject h naught at the 100 into a% level of significance if the calculated value, that is the calculated value of the f statistic, if that exceeds f a n minus k. So, the f distribution would be something like this. It is not a symmetric distribution, that would be looking something like this. So, here we have f a comma n minus k. So, if the calculated value of f is to the right of this, then we reject h naught, because most of the cases if h naught is true, the calculated value should lie to the left of this. However, if it does lie to the right, then we have reasons to suspect whether this is true. So, we reject h naught if f calculated lies to the right of f a n minus k degrees of freedom, where this has 100 into a% probability. We will take a look at another very interesting example of this application, which will be able to relate to the concept of test of goodness of fit. Students, let us now generalize this approach to the k variable model with a very interesting example. So, our model is y I is equal to beta 1 plus beta 2 x 2 I plus beta 3 x 3 I plus beta k x k I plus u I. And you will recall that this model is written in matrix form as y is equal to x beta plus u, and this vector beta is beta 1 the intercept, and then beta 2 beta 3 right up to beta k, and this was also written as beta 1 and b. So, this b represents all the elements from beta 2 to beta k. Supposing we want to test h naught beta 2 is equal to beta 3 is equal to beta 4 and so on and so forth right up to beta k, which is equal to 0. Let us say that is our null hypothesis. This we write as beta 2 beta 3 up to beta k, that is, which is equal to small b is equal to 0. This is a vector. So, our null hypothesis is small b is equal to 0. Of course, this 0 is also a vector. Okay. So, and our alternative hypothesis, let us suppose, is h1 b is not equal to 0. It means that not each of these slopes is equal to 0. Maybe 1 or 2 are 0, but not everyone is, not each one is 0. So, the null hypothesis is beta 2, beta 3, beta 4 are all equal to 0. Alternative hypothesis is not that they are all equal to 0. And let us apply the restricted unrestricted model approach, and let us see how we can connect it with what we have studied earlier. So, under the null hypothesis, we have the restricted model, and this is the unrestricted model. So, from here we estimate this. So, this is the unrestricted model, and from here we obtain the unrestricted residual sum of squares. If we now incorporate the restrictions, that means beta 2, beta 3, beta k are all equal to 0. So, in fact, y is not explained by any of these variables. So, under h naught, what do we have? Y I is simply beta 1 plus u I. So, that is the restricted model. And this will give us the restricted residual sum of squares. Let us understand what this is. Here, because you do not have any explanatory variable, so explained sum of squares is nil, and we know that total sum of squares is equal to explained sum of squares plus residual sum of squares. In this restricted model, explained sum of squares is 0, and therefore, total sum of squares is equal to residual sum of squares. So, this residual sum of squares is nothing but the restricted residual sum of squares, which is total sum of squares. So, what is the formula that we use? Our familiar formula is restricted residual sum of squares minus unrestricted residual sum of squares divided by number of restrictions q. Here, how many restrictions do we have? Beta 2 equal to 0, beta 3 equal to 0 on. so on up to beta k equal to 0. So, this q here will be equal to k minus 1. From beta 2 to beta k is k minus 1. So, we replace this q with k minus 1, and in the denominator we have our familiar unrestricted residual sum of squares. Unrestricted residual sum of squares, the model has n observations and k variable model means n minus k. So, that will follow an f distribution with k minus 1 and n minus k degrees of freedom. Now, let us probe deeper here. So, what is this? This is the restricted residual sum of squares. From which model? From the restricted model. What is the residual sum of squares in the restricted model? It is nothing but the total sum of squares, because explained sum of squares is equal to 0. So, this restricted residual sum of squares, let me write this restricted model total sum of squares, restricted model explained sum of squares and restricted model residual sum of squares. So, this restricted residual sum of squares is nothing but restricted model total sum of squares, which is nothing but total sum of squares, because total sum of squares is always summation small yi square independent of restrictions. So, total sum of squares is nothing but summation small yi square. Okay. In this case, it becomes a restricted total sum of squares. So, we can safely write here total sum of squares, and what is this? This is our familiar residual sum of squares. So, from the basic relation TSS is equal to ESS plus RSS, what we have here is TSS minus RSS, which makes this nothing but our familiar explained sum of squares divided by the number of regressors, and in the denominator we have unrestricted residual sum of squares is nothing but our residual sum of squares from the model. So, RSS by n minus k, and if you recall or if you quickly go back to the earlier module, you will find that this is nothing but this is the test of goodness of fit. So, this is the test for the overall regression which we had done earlier, explained sum of squares divided by the number of regressors k minus 1 all upon residual sum of squares from the model divided by n minus k. So, that very clearly explains why we use that formula restricted residual sum of squares minus unrestricted residual sum of squares, and that gives very nice intuitive explanation for this format. Similarly, I am going to show one or two more examples of how we do this restricted unrestricted approach. Supposing we have H naught beta 2 is equal to beta 3, not equal to 0, beta 2 is equal to beta 3, and H 1 is beta 2 not equal to beta 3. So, what is the basic model? Yi is equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I. Let us now consider the general model. So, up to beta k x k I plus ui. So, that is the unrestricted model, that gives us the unrestricted residual sum of squares. And what is the restriction here? We simply have one restriction here, beta 2 is equal to beta 3. It is not beta 2 equal to beta 3 equal to 0, it is beta 2 equal to beta 3. So, the restricted model would be yi is equal to beta 1 plus beta 2 x 2I plus again beta 2 x 3I plus up to beta k x k I plus ui. So, that would become beta 2 into x 2I plus x 3I, and then you have beta 4 x 4I plus, and it goes on. So, this is the restricted model. So, from here we will get the, this is the restricted model, and from here we get the restricted residual sum of squares. And finally, we apply the same formula, that is restricted residual sum of squares minus unrestricted residual sum of squares divided by q, the number of restrictions which is 1 here. So, that is divided by 1 all upon unrestricted residual sum of squares by n minus k, that will follow f with 1 and n minus k. And all these cases, what do? We reject H naught, at the appropriate level of significance if f calculated exceeds f critical. So, students, with that we have been able to come up with a nice test statistic for testing more than one regression coefficient jointly for the multiple linear regression model. For example, if there are q restrictions, q number of restrictions, then the test statistic becomes restricted residual sum of squares minus unrestricted residual sum of squares divided by number of restrictions q all upon unrestricted residual sum of squares divided by n minus k. Obviously, in the example that we have given just now, we have one restriction beta 2 equal to beta 3. So, this q is replaced by 1 and we have here n minus k. So, this remains n minus k and this is now f with 1 and n minus k degrees of freedom. So, I would advise you to practice this going through the study material, and we will provide you with some exercises also. Please go through the exercises and feel free to get back. Thank you.